All right, module 3.04. A lot of this stuff you'll probably remember from before, back in quarter three, before all this stuff happened, we started working from home. It's similarity. It's, side angle side. We've talked about that. We've done a lot of this. There's one thing at the end that's new, the proofs. That can be kind of challenging. We never really studied the proofs too much. Well, there's only one proof. I haven't looked at the quiz to see if there's a proof in there, but I'm sure there might be. So I'll try to explain it to you when we get there. But let's go ahead and let's get into similarity. Now, you guys kind of already know this. When you have two triangles, obviously these two triangles are not congruent, the blue one and the red one, either of this type or this type, because congruent means that they're exactly the same size. Everything about them is, one-to-one, exactly the same. Similarity is just the proportions are the same. So these two triangles, the blue and the red one, and this blue and red one, they're similar because they do have they have the same angles. You could tell that there'd be similar triangles. Their proportions would be the same, just given the fact that all these angles correspond to each other. 46.2, 46.2, right? 43.8, 43.8, 90, 90. So we know that those will be similar just because they have the exact same angles. Corresponding angles are all congruent. All right. So again, that's not something really new to us. All right. Corresponding sides. So now this part is where you get a little more mathy, right? It's kind of hard to tell just by looking at the numbers, but I mean, you can look at the picture and you can think that by looking at these two things, these two triangles, that maybe they are similar. But how can you actually calculate? How can you really determine if they're similar or not? Well, they would have the same proportions. So when I look at proportions, I like to go try to see which sides correspond to the other. Now, 1.8 is the smallest side on the blue triangle, and 2.7 is the smallest side on the red triangle. So I like to pair up the smallest side and the smallest side. That way I can, obviously those would be the ones that would correspond to each other. And it seems kind of obvious too, because they're just shaped the same direction. But we have 1.8 is to 2.7. Now we'll remember that. We'll come back to that. Look at the other proportions. We have 2.4 is to 3.6. So 2.4 is to 3.6. And then, of course, the biggest side for each triangle, the 3.4 is to the 5.1. 3.4 is to the 5.1. Now, to determine if this is all proportionally correct, that everything lines up as it should, we would just calculate this to see if all those fractions end up being the exact same proportion. So I'm going to pull up my calculator real quick here. It's going to take a second to load up, but you'll see how I determine whether it's congruent or not, now or similar or not. So our first one was 1.8 to 2.7, right? So I would just type in, 1.8, not 1.5, 1.8 divided by 2.7, and I get, 0.66 repeating, right? If I did the same thing for the other ones, 2.4 divided by 3.6, oops. I get the same thing. And then the last pair, I got the 3.4 divided by the 5.1. 5.1. And it gets me the exact same thing. So since all three fractions, all three pairs of angles match, then you know that each side is proportional to the other and that these two triangles are similar. So that's how you would test to see if the sides are proportional. So if the angles are all the same, like we saw on the first page, then they're similar triangles. But if the sides, the sides don't have to be the same, because remember, it's not going to be congruent. The sides just have to be proportional. So as long as the sides are all proportionally the same, like these sides were 0.66 repeating, then you have a similarity. All right, so some practice problems. Practice 1, just determining which side corresponds with what. So side AB. So side AB is this side here. And for the other triangle, I would say it corresponds with EF, right? For side BC, I would say that BC, which is the top here, corresponds with FG. And then the third question says which angle corresponds with angle D. So angle D is the one down here. I would say that angle H is the one that corresponds with that. And for angle B, I would say angle B corresponds with angle F, right? Just kind of making a matching, just finding out what part corresponds with what, essentially. All right, practice 2. Are they similar? Is the first triangle, or not triangle, the rectangle, the bigger one, is it similar to the smaller one? And the one way we can check again is using the proportions, right? Because we already know that angles are all the same because they're all 90-degree angles all the way around. But we have to make sure that the proportions are the same too. So for proportions, let's look again at the biggest side to the biggest side. So that's the 25 to the 15. So I'm going to line those up with each other. 25 is to 15. And then we have the smaller side with the smaller side. 5 is to 3. So I'm just going to go back to my calculator again. And see if I get the same results, right? So 25 divided by 15 equals 1.66 repeating, and then 5 divided by 3 equals 1.66 repeating. So that confirms that these are similar because they have the same proportions. So I think you guys kind of get the idea for the most part. We did pretty well with this back in March, February, whenever we studied all this stuff. Okay, now since these are similar, right, it's literally telling you that they are similar. It wants you to find the value of x. So here's a simple way to do it. Remember, we have to line up our proportions. So let's go with the biggest side to the biggest side. So the 12 on the big trapezoid is to the x on the small trapezoid. And since they're already similar, we know that they would be equal in proportion. Let's line up the small sides to the small sides. So we got 4 is to 2. Okay, now it's important that we set this up correctly. You'll notice that on the top here, I have the values of the left trapezoid, and on the bottom part, I have the values of the right trapezoid. Everything's lined up the same. I can't undo that, so I'll just have to erase this because I scrolled all over it. But anyway, we have 12 is to x as 4 is to 2. Let me go back. Right, 12 is to x as the 4 is to 2. So again, that's simply the biggest side on this trapezoid to the biggest side on this one, and then the smallest side on this trapezoid to the smallest side on this one. So everything's lined up. Now we just have to cross multiply. It's pretty simple. So 12 times 2 and x times 4. So 12 times 2 is going to make 24. And 4 times x will be 4x. So then we just divide by 4. My computer is getting really laggy now with my calculator open, but it's fine. Divide by 4 and you get x equal to 6 as your result there. All right, it's a shame I have to erase this. Maybe next time I'll just take a screenshot. As you guys just fast forward 10 seconds. All right, let's move on to page 4. So, I mean, similarity in a nutshell, we kind of already have a decent understanding of. Dilations is the same thing as similarity. It's just being multiplied by a certain factor. So you see these two triangles here, the small one and the large one, they're similar. And the question really is, what's the scale factor? So we're going to calculate the scale factor. Now, this one already is a scale factor of 2. And we can kind of tell that because to go from the small triangle to the big triangle, you can see to get from 3 to 6 or from 4 to 8, you have to double it, right? So you have to multiply it by 2. So the scale factor is obvious in this one. But in the next few problems, we'll try to calculate what the scale factor actually is. Because it won't tell us. It'll just ask us to find it. All right, but before that, I guess there's not an example for us right away, but we have angle similarity. So angle similarity says that if you have two triangles, and this applies only to triangles, not to trapezoids or rectangles or anything like that, only to triangles. If you have two angles that are the same for two triangles, that those triangles are similar. So you see on these triangles, they have one matching pair that's 83 degrees, and they have a second matching pair that's 63 degrees. And since they have two matching pairs, those triangles are similar. We don't need any more information than that. We don't need to know any of the lengths of the sides, nothing. That right there is enough information for us to determine that those two triangles are indeed similar. That AB is proportional to DE, that AC is proportional to DF, right? Everything here is proportional. The entire triangles are proportional and they are similar. So angle similarity. All right, let's see if we can determine if the two triangles are similar. So if we look at this first example, I'm actually gonna do the snip this time. All right, if we look at this first example, notice we see the triangles, they have matching pairs. They have 27-degree angle here and a 27-degree angle here. So that's one matching pair. And they also have a second matching pair, 58 degrees, 58 degrees. Obviously, the triangles are kind of turned, but they do have two matching pairs, right, of angles, which means that, yes, they are similar by angle similarity. So not a hard problem, that one, because it gave us pretty much all the information we needed from the beginning. But if we look at this example, it's a little bit different. So we notice right away, of course, they do have one pair of matching angles. That's the 90-degree angle, right? So they have one matching pair. But you might think that they're not similar because the 48 does not match the 42, right? So they don't have a second matching pair. But you'd be wrong in thinking that that's all you'd have to do. Because what if the 48 isn't actually corresponding with this angle? What if the 48 is corresponding with this one, right? What if that angle is 48? Because if that angle is 48 degrees, then you have, your second pair of angles that match. And of course, same thing can be said for the 42. The 42 might be paired up with this one. How do we know, right? So here's what we do. Remember, one rule of thumb is that the sum of the angles in the triangles all add up to 180. So we know that this right here is 90 degrees. We know this right here is 42 degrees. And then the last angle that it does not give us, I'll call it x. But I know that when I add up all three of those numbers, I would get 180 degrees. So when I calculate, 90 plus 42 is 132 plus x equals 180. And then I can subtract the 132. And I end up with x equal to 48. So it is true indeed that this angle up here is 48 degrees. So it didn't tell us that right away. We had to do a little bit of math to find it, but guess what? Now I've got two pairs of matching angles. I got the 90-degree pair that counts, and I've got the 48-degree pair that counts. So since I have two angles that are the same, it is angle similarity again. And if you wanted to do the math, you can also find out that the 42-degree angle does match with the other side. So if you wanted to kind of work that out instead, 90, if you did the other triangle, 90 plus 48 plus the third angle C equals 180 degrees, you'd get the same result, but you'd get 42 as this answer. So 90 plus 48 is 138. And then you would subtract 138. And you get x equal to 42. So that would tell us that this angle here is 42 degrees, which again, of course, matches this one. So you can find all three angles if you want, but remember, you only need two angles to prove angle similarity. And then the last one, let's try this one out. So again, we can see I've got one matching pair. I've got the 46 degrees matches the 46 degrees. Obviously, I don't have the second matching pair, but let's do the same trick as before, because maybe this is the 67 and maybe this one's the 55. So let's do the math, right? So remember, all angles in a triangle add up to 180 degrees. So that means for the first one, we have 46. Oops, not 14. I don't know why we're that. 46 plus 55. We'll call this one x. Plus x equals 180 degrees. So when I do the math, I end up, this is 101. Correct? Yeah, 101 plus x equals 180. So when you subtract 101 from both sides, you end up with x equal to 79. So that tells us that the angle here is 79 degrees, which does not match the 67. So there's no way I'm going to be able to get a second pair of angles that'll match. You can check the math on the other way around. You can try to find angle F here, but it's not going to match the 55. But we can always check. So for that triangle, we have the 46 plus the 67 plus x, which is our angle F, equal to 180. So you can double check if you want, but this I don't think gets us the answer we desire. So I don't think these triangles are similar. 46 plus 67 is what? 113, I think. And then if you subtract 113 on both sides, you end up with x equal to 60. Is it 67 again? It's 67, I believe. But at the same time, 67, that's not a match for any of these triangles over here or any of those angles over there. So I don't have any double matching pairs. I only have the 46 is the only angles that in these triangles that will match. 55 doesn't match with anything over here. And what was 79 here does not match with anything over here. So there's nothing else we can really do. Those triangles are not similar. All right. Side angle side postulates. So, of course, we talked about similarity already. We have to have the congruent angles, the same angles, of course, but also have the proportional sides. All right. So we know, obviously, the scale factor of this one. These two triangles here are exactly the same size. So the scale factor is 1, meaning that you would multiply all these values here, the 2 by 1 to get 2, the 2.5 times 1 to get 2.5. So scale factor being 1 means it's exactly the same. But let's see if we can find the scale factor of these two triangles. So the question is, what number would you multiply 2 by to get 3, and what number would you multiply 2.5 by to get 3.75? So in order to calculate that, what we can do is just take the bigger one and divide it by the smaller one. So 3 pairs with the 2, so we can divide those. 3 divided by 2. And the 3.75 pairs with the 2.5, right? Because they're proportionally, they are what matches. So if we get the same decimal value here, then we know that these triangles are similar, but also whatever the value is that we get is our scale factor. So if we take 3 divided by 2, we get 1.5, and if we take 3.75 divided by 2.5, we get, same thing, 1.5. So our scale factor is 1.5, and the two triangles are similar. So our scale factor for that one was 1.5. So if we check the answer here, it should say 1.5, right? This one's a little more obvious. You can actually, if you see how do you get from the small one to the big one, from 2 to 4 and to 2.5 to 5, scale factor here is just you're doubling it, right? So scale factor there must be multiplying by 2. And also side angle side postulate. This means that if you have, we talked about side angle side in class before, but a side angle and side where everything is proportional, like here, the 2 and the 3 were proportional, and the 2.5 to 3.75 were proportional, and the angles matched. This is similar triangles based on side angle side. So it's got the two sides and the angle between the two sides, and everything is, of course, a matching pair. All right, so the side angle side stuff again. So again, we've already talked about this. For side angle side to work, you'd have to have two sides for your triangles and the angle between them. So you can tell that these two triangles are similar because the 5 and the 10 are proportional. The 5 to 10 is doubling, and the 3 to 6 is doubling, so that we know the sides are proportional, and they have the matching angle between the sides. So that's two sides and a matching angle. So side angle side. Similarity. If we want to try an example here, are the two triangles similar? We could say yes again. Notice they've got the pair of sides. 6 is to 3 as 4 is to 2. You'll notice that 3 is half of the 6. 2 is half of the 4. So that proportionally lines up. And the angle between the two sides on both of these is the angle that matches. So again, we would have, yes, side angle, side triangle there. This one's a little more interesting. It doesn't label it for you, but it does give you all the values. You have a kind of a triangle inside of a triangle. You got the smaller triangle here, and then you've got the larger triangle here. So you have like a triangle inside a triangle. So BH is 3, but BG is 4, and BA is 6. So this whole thing is 6, and then BC is 8. So we'd have again, the 6 is to the 3 as the 8 is to the 4. And you'll notice that 6 is to 3 is 2, 8 is to 4 is 2. So they do pair up evenly. They are proportionally the same. And they even, share the exact same angle. Because you'll notice that for the small triangle, we have the side, and the angle between it is 103. But for the bigger triangle, we have this side, and the angle between it, again, being 103. So you've got the side, and the angle between it, meaning you, of course, have side, angle, side, similarity. All right. Just to save some time in the video, I'm going to let you guys look at those examples. I guess maybe I'll do one. And then if you guys want to practice the rest, remember you can always check your answer here. It does give you the answer, but let's make sure that you know how to do it real quick. So immediately, what I notice is I have side angle side. I just have to concern myself with, is everything proportional with each other? You'll notice for the big triangle, I have side, and the angle between them. So side angle side is here. And for the smaller triangle, I have a side, and the angle between them. So again, I have side angle side here. So I already know side angle side is there, but I need to make sure that everything is proportional. So to do that, we can already see the angles are proportional, so there's no worries there. But let's see if the sides are proportional. So the longest side here is 6, and the longest side for the bigger one is 21. So 6 is going to pair with 21. So if you're wondering, how do I know 6 doesn't pair with 14? Well, again, that's why I said the longer side. 6 is bigger than 4. 21 is bigger than 14. So the biggest number here and the biggest number here have to be the ones that line up. Of course, then we do the same thing with the smaller numbers. The 4 is like the 14. It's the smaller on each of the triangles. So the 4 is to the 14. So now I just have to see if these are equal to each other. So a quick way of doing that is just taking the calculator and doing 6 divided by 21 and 4 divided by 14. And oops, I hit times. Meant to hit divide. 4 divided by 14. Yes, you do see that the 0.2857 is the same. So because they are proportionally the same value, that means that these two triangles are similar. And remember, it already established side angle side, so we knew that was good. We just had to check to see if it was proportional. It wouldn't really matter if it was proportional and it wasn't side angle side. So make sure you have both of those things, the proportions and the side angle side. So these all work the same. You'll probably notice you got to be real careful on practice problem 2. I knew I said I was going to let you guys do it, but I want to point this out. This one, you should be really kind of throwing away immediately. When you look at this smaller triangle, you've got this side, and you have the angle between it. So that's good, because then you have side, angle, side. But if you look at the larger triangle, we have this side and this side. The angle we're given is not the angle between them. The angle between them would have been angle F. So the fact that the angle is not between the two sides means that this one is not side, angle, side. So therefore, there's no reason to go about doing the rest of the problem because you're not establishing side, angle, side here. It doesn't matter if their proportions are the same. It's not side, angle, side, which is what we wanted. So that one's not going to be similar. That answer is going to be no. It's not possible to determine, right? So be on the lookout for something like that. Let's look on page 8. So side, similarity is kind of the same thing. Side, angle, side, except you're just looking for all three sides to match. So when you look at your first problem here, this first example, you've got all three sides of two triangles. So again, pair the smallest with the smallest, the largest with the largest, and then the middle side with the middle side. So the smallest side here is 1, the smallest side here is 2. So the 1 is to the 2. The next smallest side is 1.17, and the next smallest side here is 2.34. And then, of course, the largest side is 1.5, and the largest side here is 3. So as long as you do the division, 1 divided by 2 is 0.5. 1.17 divided by 2.34 is also 0.5. And 1.5 divided by 3 is again 1.5. So they would all match, and they would all be proportional, which means that these two triangles would be similar. Same thing on this one, of course. Small with the small, so this one would have the 1.7 pair up with the 3.4. Then the next smallest, so 1.81 to the 3.62, and then the largest to the largest, 2.3 to 4.6. And when you make all those pairs line up, again, all of those end up being 0.5 as well. So if they're all three equal to the same value, then they're similar triangles, which is good. All right, side, postulate again. I guess it gives us some examples here. Is triangle ABC similar to triangle DEF? And just by looking at it, it looks like it would be yes, because the smallest side, 1 to 2, 1 is half of 2. And when you look at the other sides, 2 and 2 and 4 and 4, well, 2 is half of 4. So that does seem proportionally like it would line up. Without having to do any math, we could probably figure that out in our head, because we can tell what's double or half of one other thing pretty easily. So is triangle ABC similar to triangle FDE? All right, let's talk about this one. Now, I noticed small side here is 5 and the small side here is 2, so 5 to 2. The next smallest is 4 and 10, so 4 to 10. And then the next smallest is 6 to 15. Oh, I did that backwards, by the way. Notice, see what I did there? I went from 5 to 2, so I went from this triangle to this one. But the second time around, I wrote it backwards. So make sure it's all consistent. If I'm saying 5 is to 2, then I'm saying 10 is to 4, and I'm saying 15 is to 6. All the numbers on top start here, and all the numbers on bottom end in the smaller triangle. So let me make sure I have that right next time. So 10 is to the 4, and then 15 is to the 6. And when you divide all these, this ends up being 2.5, this ends up being 2.5, and this one ends up being 2.5. So it's good, it has all the proportions, but here's something I want to point out real quick. The way you write this answer, and this will be said something a little bit later in this module, but I want to point it out now. So triangle ABC, is similar to triangle, and it says FDE. Now, I've talked about this in my class before, but in order for this to be a true statement, everything has to line up the way you'd want. So what I mean by that is that notice AB is the first two letters here, and FD is the first two letters here. That means the side AB should correspond to the side FD on the paper. So the side AB corresponds with the side FD. And as we noticed, that's true. We said the 5 was with the 2. So that's good. If you also look, you would look at BC being the second and third letter and DE being the second and third letter. That means that side BC should correspond with side DE. So BC is this one, and DE was this one, the 10 into the 4. And we already mentioned that as well. And the last one, which we're not going to point out, but would be the AC side and the FE side. They would all match too. And the reason I'm pointing this out is because this is the only way, well, not the only way, but you'd have to make sure that when you write out your similarity statement that it's lined up intentionally. So for example, what I want to show you is something that'd be wrong. You wouldn't want to say triangle DEF here. This is no longer a true statement because now you've mixed up the proportions. When you write something like this, you're claiming that AB corresponds to DE. And as we know from looking at this, that AB does not correspond with DE. That side didn't correspond with that side, right? That's false. So it's important that we put this in the correct order to say which one corresponds with which one, which side corresponds with which side, which angle corresponds with which angle. So saying FDE and not anything else like DEF, that's the correct way of saying it. Okay, writing it like this. So make sure the letters, the order of your letters matters. It really, really does. Okay, it has to make sure it lines up and pairs up with the original one. All the sides pair up, all the angles pair up. So determine whether these are similar. So the smallest side here is 2. The smallest side here is 4. So 2 to 4 is doubling. Then 3 to 6, which is doubling, and 4 to 8, which is doubling. So yes, those two triangles do seem like they would be similar. Yep. All right, now if you want to solve it, let's see this one. So it says that these triangles are similar. So it wants us to solve for x. So here's what we would do. All right. So let's try to figure out which matches with which. So that's kind of the hard part. I would say the smallest side here is 24, and it pairs with the small side here being 36. So let's find out what the scale factor is from this. So 24 is to 36. So that would be 0.66 repeating, right? Okay, so there's your scale factor. In order to get from this triangle over to this triangle, well, actually, if you did it the other way around, no, yeah, if you did it that way, you'd have to multiply these values by 0.66 repeating. So 36 times 0.66 gets 24, as we've already established. Let's try it with the other one. So let's try 84. 84 times 0.66 repeating. So let's take our calculator out. So 84 times 0. I'm going to type this out as much as I can because I don't want it to round too much. So we'll just say that. Put a little 7 at the end, make it nice. We end up with 56. So that's telling me that this is matching to this one. So the 84 matches to the 56. And so to find x, we do the same thing, but with 66. So we're going to multiply this one times our scale factor of 0.66 repeating, and that should give us x. So let's type that out. So 66 times that scale factor of all those 6s, maybe a 7 at the end, just to make it nice. All right, is 4. Oh, I put a 0 in the wrong place. Do you see that, where I made that mistake? I can't tell if you can tell it. Well, let me type it in one more time. It's times point. There you go. See, I didn't put that 0 in this time. There you go. That's good. And we get 44. So that means that x has to be 44. So just to quickly sum up what I did, I took one pair that was obvious to me, which was the smallest sides. okay, I took the 36 and the 24 in order to find the scale factor. So I divided those to find the scale factor. So 36 times the 0.66 repeating would get me 24. And so I just applied that same scale factor to these other two. I found out the 84 actually pairs with the 56, and the 66 actually paired with x in order to figure out what x was. All right. I guess I'll leave that one for you guys. Let's try. I think the next one's a proof. No, the next page I believe is proof. All right. So triangle proportionality theorem. So basically, what this is going to claim is when you have two parallel lines or two triangles, but the two edges of them are parallel. So, like for example, you'll see here the smaller triangle here, and then the bigger triangle here. Obviously, we can see that these sides are overlapping each other, but if this side is parallel with this side, and you'll know it's parallel by seeing like these little arrow marks. If those lines are parallel, then that means that these two triangles, the small one and the large one, are going to be similar triangles, but only if these lines are parallel. Okay? And that goes the other way around as well. If I told you that these triangles, the small one and the large one, if I told you they were similar, then that implies that those two lines would be parallel. Okay? So it's here on this page, it's kind of just showing you the proportions. It's taking the proportions and lining them up. And then it's showing you that if you cross multiply them, you get the same value. So like for this problem, let's do this one real quick. 1.6 is AD and 2.4 is AB. So 2.4 is the whole thing. AE is 3.4 and AC is 5.1. So it's saying, 1.6 is to 2.4 as 3.4 is to 5.1, right? It's lining up those proportions, but instead of actually dividing them, seeing if they're the same, what they're doing here is what they're actually just cross multiplying. So saying 1.6 times 5.1 is equal to the same thing as 2.4 times 3.4. Cross multiplying, and you can take your calculator and you can prove that if you cross multiply you get the same. So 1.6 times the 5.1 is equal to the 8.16, and the other cross multiplying 2.4 times the 3.4, you also get 8.16. So cross multiplying gets you the same values if you divided them. So if you divided them like we normally did, normally we did 1.6 and then we divided by 2.4. But you don't get the same number. You're not going to get 8.16. But the point is you want to see if they match. You want to see if they're the same. So if we took the 3.4 divided by the 5.1, again, you'll see that we still get the same matching number. So it's proportional, again, if everything matches. This right here is just showing you that you can cross multiply them and to figure out if they match. You don't have to just divide them and see if they're the same value. You can cross multiply them instead if you find that easier. And if, again, they're the same value, then they're proportional. So all these do that. So I won't show you all of them. You can click on all of them if you want. But now let's look at our proof. So this is something we haven't talked about before. So a proof works by taking what information is given to you and finding a next step in the process until you come up with your conclusion. So it wants us to conclude that AD is to AB is equal to AE to AC. So in order for us to do that, let's read what we're given. So right here, we're given the triangle ABC. We're given a triangle DE intersects AB and AC. So we're talking about, let's see, this line here intersecting AB and intersecting AC. And then it's also saying that the lines are parallel. DE is parallel with BC. So DE here is parallel to BC. And we can see that because it's got little arrow marks. Now, Statement. Triangle ABC is intersected by line DE. So that's already given to us. That was true. It said it in the beginning that we had those intersections. So for this, I'm going to say that was given. Usually the first one or two lines is given because it's literally something that was already set up here. So for example, the next part says DE is parallel to BC. Well, guess what? Again, that was given because it literally told us that at the beginning of the problem. So that's given to us as well. But now we're talking about something new. Triangle ABC is congruent, or not triangle, but angle ABC. I'm going to need to write this down. Angle ABC is congruent to angle D, ADE. So ABC, angle ABC. So ABC, we're talking about this angle here, essentially angle B, is congruent to ADE. So let's look at that, ADE. So that's going to be this angle here. So it's saying that those two angles are congruent. And because these two lines are parallel, that's true. But the reason why that's true is based on, let me go to it, the fact that they are corresponding angles. So corresponding angles postulate. You know, we've talked about this before, that angle D for the small triangle is corresponding with angle B in the big triangle because they are essentially pairs. They are matching angles just in different triangles. Now, for the exact same reason, the next statement is for this, also corresponding angles postulate. So if I kind of explain that one, this is saying angle ACB. So angle ACB, which is going to be this wedge here, is congruent to AED. So AED, again, is this wedge here. So it's saying these two angles. And again, yes, they are congruent because they are corresponding angles. Angle E does correspond with angle C. They're just in separate triangles. Okay, and again, we know that because of the parallel lines. You guys will learn a lot more about that in geometry next year. So because we've established all of those things, we've established that angles are congruent to each other and all the fact that stuff that was given to us, we know that these two triangles are similar. We can say that these two triangles are similar by the angle postulate, because what we've just done is we proved the angles are congruent. So I'll just write it on here. We proved that we have one pair of angles congruent right there, and we proved a second pair of angles are congruent right there. So that's two pairs of angles that are congruent, which, as we talked about before, means we have similar triangles. Angle similarity. That's what we talked about at the beginning of this. So we can make our final conclusion that the sides are corresponding to each other, and we can say that simply based on the definition of similar triangles. So now that we know the triangles are similar, that means all the parts are corresponding are similar. So that's why we're saying definition of similar triangles. Submit it, and we got it all right. It's tricky, those proofs. So, maybe you want to practice a few more. They don't give us any more practice problems than that, but that's all we can do for it. I'm not going to go through this, the Pythagorean Theorem. Basically, what this is, though, we have kind of right triangles inside right triangles, which is pretty cool. So you'll notice that this right triangle here, well, we cut a line down the middle. We can make another we can actually make two more right triangles. You'll notice we have a small right triangle, and then what I like to call is the medium right triangle, all inside the large right triangle. It's kind of how I look at it. And then, of course, this just kind of breaks it all into those three triangles. You have the small, the medium, and then the overall large one. And the funny thing about it is that they're all similar as well. Each triangle is similar to the other. The small is similar to the medium, similar to the large. All three triangles are similar. Again, if you don't see three triangles, remember you've got this very small one here. Then on the other side of that, you've got the medium one. But then the entire thing, remember, is a triangle. So you've got your large triangle, right? That one. So it's just trying to show you that they are all similar triangles, which is cool. And that's going to be it. I mean, that covers it for this section. So I'll let you guys kind of do the work, try out the quiz. If you have questions, remember to let us know. And I'll see you in next week's video.